Good morning to all of you. In previous session, we discussed about rational set transform, as well as we have seen one example where we have obtained the pole zero plot by identifying the pole and zeros from the obtained set transform, right? So in today's session, we'll be discussing pole location and time domain behavior of causal signals. Okay, so depending on the pole location, we can identify how signal is behaving, right? So here we'll be discussing pole location and time domain behavior of causal signals. As we know that in case of causal signals, even in case of causal systems, okay, the characteristics of the discrete time system depends on the current input sample and the past input sample, but it does not depend on the future input sample. Okay, so in this case, the characteristic behavior of causal signals depends on whether the poles of the obtained transform are contained in the region. So we can consider that the region is mod z less than 1, or it can be in the region mod z greater than 1, or on the circle, right? That is mod z is equals to 1. Okay, so depending on these three conditions, right, that is, if poles are in the region mod z less than 1, if poles are in the region mod z greater than 1, or if poles are on the circle, that is at mod z is equals to 1. So basically, when we are saying that uh, we are drawing a circle with radius 1, okay, in this all these three conditions, in all these three conditions, we're comparing the pole's location with value 1. Okay, so that means we are plotting a circle with radius 1, so that will be called as what? A unit circle. Okay, so we'll be plotting a circle with radius 1 and we are calling it as a unit circle. Okay, so it will be referred as what? Unit circle. So we are simply defining the characteristic behavior of causal signal by taking into consideration the location of poles with respect to the unit circle. Okay, so depending on this, the signal can be decaying. These causal signals can be decaying, or it can be fixed, or it can be growing. Okay, so the signal is decaying. Okay, if pole is inside the unit circle. Okay, so that means if there is unit circle, right, and if this pole is inside this unit circle, okay, this circle were drawn with radius 1, right, and if poles are inside this circle, then the signal is decaying, right, and if the pole is on the circle, then basically we have seen in the previous session these poles can be denoted by using cross, right, while zeros are indicated by using circle, right, by using cross for poles and for zeros we are using circles, right? So if these poles are on the unit circle, right, so then that signal will be called as what? Fixed signal. Okay. And if the pole are outside this unit circle, right, so then the signal is growing one. Okay. So the signal is decaying if pole is inside the circle. It is fixed if the pole is on the circle, and it is growing if the pole is outside circle. Okay, it may be anywhere outside this unit circle. Correct. So in that case, the signal is growing. Okay. So same conditions are indicated here. That is, the poles are inside the circle, then it is decaying. The causal signals are decaying. If poles are outside the unit circle, then it is growing. And when poles are on the circle, then it is fixed. Okay, fixed. So causal signals with poles outside the unit circle becomes unbounded. Okay, so causal signals with poles outside the unit circle becomes unbounded. Right. So, and these unbounded causal signals can cause overflow in discrete time systems or digital system. Okay, so these unbounded signal can causes overflow in discrete time or digital systems. So therefore, these unbounded signals must be avoided. Okay, there should not be some signals or having those signals should not be unbounded, or their pole should not be outside the unit circle. Okay, so causal real signals with simple real poles or simple complex conjugate pairs of poles which are inside or on the unit circle are always bounded in amplitude, right? So basically the causal signals with simple real poles or simple complex conjugate pairs of poles which are inside, okay, or on the circle, on the unit circle, okay, are always bounded. So basically the bounded nature of these causal signals can also be identified by using the pole location. So if poles are outside the unit circle, then causal signal become unbounded, and if the poles, okay, the causal signals having poles, those poles may be real or those may be complex, right? So if those poles are inside or on the unit circle, then it becomes bounded. Okay, the causal signal become bounded, right? So this is how we can define the behavior of causal signal, time domain behavior of the causal signal depending on the pole locations, right? So basically, zeros can also affect the behavior of a signal, but not as strongly as poles, right? So this point you can also note it down that zeros can also affect the behavior of a signal, but not as strongly as poles, right? So therefore we are discussing here topic, or we are considering, whenever we are considering causal signal, we are focusing on the location of poles, right? So here we have seen, if the poles are inside the unit circle, then signal causal signals can be decaying. If those poles are outside, then causal signals can be growing. And if the poles are on the unit circle, then it is fixed, right? And depending on the pole location, if those poles are outside the unit circle, then causal signal can be unbounded, and such signal or signals having poles outside the unit circle should be avoided to avoid the system overflow. Okay, and similarly, if the poles which are simple poles or maybe complex poles which are inside the unit circle, or those poles location are on the unit circle, then those causal signal can be or always be bounded signal, right? And zeros locations are not considered because zeros location cannot affect the behavior of signal as strongly as the poles. Okay, zeros location can affect the behavior of signal, but not as strongly as the pole locations. Okay, so in next session we'll be discussing the system function of a linear time invariant system. Right? So thank you for joining this session.